Thank you. First of all, I would like to thank the organizers for inviting me to this wonderful conference. And I would like to present here my last work, which I did together with Atakan Firat, Monkey Kim, Ashok Sen, and Bogdan Stefansky, who is here at this conference. And actually, this work is one in a series of papers where we studied D-instanton effects in various string compactifications. So therefore, let me start from some motivation why it's interesting to study such D-instanton effects. At first, let me recall that D-instantons in string theory, they appear typically as D-branes wrapped on non-trivial cycles of the compactification manifold, and already this fact implies a lot of interesting relations to some various geometric problems. But also from the physical point of view, well, on one hand, we know that instantons, they're exponentially suppressed in the small string coupling limit, so one might think that not so important, but actually they are important. For example, we know that they're crucial for non-perturbative string dualities, and if at some point we hope to go beyond perturbative formulation string theory, we must take them into account. Then, if we turn to various string compactifications, for example, let's consider compactifications with n equal 2 supersymmetry in 4 dimensions, then it's well known that these instantons, they contain information about various numerical invariants of the compactification manifold, and in turn, these invariants, they encode, for example, entropy of various BPS black holes. And so studying instantons, you can obtain some non-trivial information about these black holes. For example, just to give you an example, a few years ago, together with Boris Pulin, we showed, precisely by studying instantons, that generating functions of degeneracies of D4, D2, D0 black holes generically behave like mock modular forms, or more precisely even high depth mock modular forms, and we were able to derive an explicit form of the modular anomaly, and from the study of the instantons. So this is just an example how it can be useful. And if we go further, further break supersymmetry and consider n equal 1 compactifications, then we know that instantons, they're essential for moduli stabilizations, because some of the moduli can only be stabilized if you take into account these instantons. But despite this importance, and in contrast to the case of gauge theories, until just 2 years ago, there was a problem because we could not really compute these instantons just from string amplitudes. Well, we could, but typically all these amplitudes were, they suffered from various ambiguities in divergences, which typically came from various zero modes associated to the instanton. And breakthrough happened when Ashok Sen, he understood how to deal with all these zero modes and produced certain recipe how to deal with them. And then once he derived this recipe, he applied it first to non-critical string theory in 2 dimensions, then to type 2B in flat 10 dimensions, and then me, Ashok, and Bogdan, we considered computations of type 2 string theory and Calabi-Yau threefolds, and computed instanton corrections in that situation. So all these 3 cases, they characterized by the fact that there were already predictions for the D-instanton effects in these theories on the basis, well, either matrix models in the case of non-critical string theory, or various dualities like S duality, mirror symmetry, wall crossing. And it turned out that in all these cases, there was a perfect match between the predictions based on matrix models or dualities and these computations of the amplitudes based on the recipe of Ashok Sen. And our goal was then go further, because now we see that this recipe has a solid ground. it passed many non-trivial checks. So let's try to derive something new, namely go to the case where there were no predictions based on dualities, and this is the case of orientifold computations. And in this case, we derived the so-called D-instanton induced superpotential, and the goal of my talk will be to present these results. Of course, I should say from the very beginning that this D-instanton induced superpotential was considered long ago by many, many people, and many of these people sit in this room, but our modest contribution was really to understand the concrete numerical factor which appeared in front of this superpotential, which was not, it was not possible to compute it before. But before going to this story, nevertheless, I want to return to this situation and show how what really was the check which we did in this case of type 2 strings on Calabi-Yau. Because you see that there the situation is quite non-trivial. So in this, when we consider just type 2 string theory on Calabi-Yau threefold, well, it's well known in 4 dimensions we get an effective theory, which is n equal to supergravity coupled to matter, and at the 2 derivative level, the effective action is completely captured by the metric on the modular space of the theory, and the modular space is known to have this factorized form. So the first factor, the vector multiplet modular space, is a very boring guy because it's a special Keller manifold. The metric on this manifold doesn't receive any corrections in string coupling, so we know everything about it. The other guy is much more complicated. So this is a hypermultiplet modular space. First of all, it carries quaternion Keller geometry. It's not, so this geometry is much more complicated. It's not even Keller, so the name is somewhat misleading. And it's known that the metric receives corrections, both perturbative and non-perturbative, in string coupling. In particular, it receives corrections from D-brane instantons. The good news is that actually already long ago we understood how to incorporate all these D-instanton corrections to the metric, and exactly, namely to all orders in the instanton expansion and exactly in string coupling. This was originally done using the so-called twistorial techniques, namely as deformations of the so-called holomorphic contact structure on the twistor space built over the original modular space. This construction, in fact, if you know, for example, construction of Gayota-Murnaitsky for instanton corrections for n equal to 4-dimensional gauge theories compactified on the circle, so this construction is very similar to that. Just the difference is that they deal with hyperkeller manifolds and we deal with quaternion Keller manifolds, which are somewhat more complicated. But otherwise, it's a very elegant, nice construction, but still it's somewhat inexplicit because at the end of the day, we're interested in the metric, and although this construction fixes the metric on the modular space uniquely, well, it's actually very painful to compute it explicitly. Nevertheless, a few years ago, in my paper with Sebastian Banerjee, we managed to do it. And so now we have this D-instanton corrected metric explicitly computed. But it's very huge and complicated, so horribly looking, so I don't even want to show it here. But fortunately, we don't need this full metric, because what we need is just the leading approximation in the small string coupling limit, because this is what we will compute from string diagrams. And it turns out that in this limit, the metric considerably simplifies. Well, it looks still a bit complicated, but well, I will not explain all notations here, just let me explain the main structure of this metric. So the instanton contribution to this metric is found to be like, there is a sum over all D-brane charges, then there is some factor, then the second factor describes the so-called multi-covering effects, where the D-brane wraps the same cycle k times, and finally, there is the last factor, and if you drop terms proportional to the differential of the instanton action, the claim is that this factor can be brought to this quadratic form. So it's just a square of a certain one form, which I showed here explicitly. But what is important is just fixed by D-brane charge and prepotential. So, of course, since we knew the exact metric from the very beginning, we also know the terms which I dropped here, but we will not be able to compute them from string amplitudes, and therefore for our purposes, they're useless. So therefore we can drop them, and then we have this nice quadratic structure of the metric. And the claim is that this metric should also come out from the computation of string amplitudes. And the claim that it does, and one can show that the same metric appears as the following combination of string diagrams. You see there is exponential of the annulus amplitude with the boundary on the D-instanton, and then there are two 3-point functions with one insertion of a closed string field operator and two fermion zero modes at the boundary. And the claim that if you compute these annulus and disk diagrams, which is of course very painful, but one can do it. It involves some CFT calculations, then a lot of Calabi-Yau geometry. In the end, you recover precisely the same expression which I showed on the top of this slide. And it comes out with the right signs, right coefficients, so everything works. And both in type 2A and type 2B, because, well, of course, the two formulations are related by mirror symmetry, so you should reproduce the same metric up to field redefinitions, but the point is that the computations of these amplitudes, they are very different in the two formulations, and nevertheless, you always come to the same expression. So it looks like a miracle, but probably people who work in this field, they already should be used to such kind of miracles, so this you constantly find them here. Let me just, let me note that here we reproduce not just a coefficient, not just even a function of moduli, but the whole metric. So, namely symmetric tensor with a very non-trivial dependence on all the moduli fields for all components. And just the final comment here, which I would like to do, is that if you look at this expression, you could think that we're computing a two-point function here, because there are just two disk diagrams. But if it was the case, we would have troubles, because you see here in the denominator, we have p dot p prime, where p and p prime are momenta of these closed string vertex operators. And if we computed a two-point function, then would have to impose momentum conservation, would get p squared in the denominator, and here we have massless fields, so p squared would be 0, and well, this expression would be nonsense. The point is that we are not computing two-point function. This expression really appears as a part of a four-point function. Well, I don't have time to explain how it comes about, so if you are interested, you can either ask me later or look at our papers. So I hope I convince you that there is a really non-trivial consistency check between two approaches, namely one based on dualities and another one based on this recipe produced by Ashoksian, how to deal with the zero modes in the presence of D-instantons. So now probably we have a solid ground, so let's try to do something new. And for this, we will consider orientifold complexifications of type 2 string theory. So let me first explain you the setup which we took. Actually, this is the most simple setup one could imagine in this situation. So we take type 2B string theory, compactified on a Calabi-Yau threefold. We add some orientifold planes and space filling D-branes so that to cancel the tadpole, but we don't introduce any fluxes, so just to avoid any complications with them. And then we assume that there is a cycle, there is a divisor on the Calabi-Yau, which will be wrapped by Euclidean D3 brane, and this divisor has the following properties. So first of all, it's invariant under the orientifold projection, and secondly, it's rigid. So in this case, our instanton is known like rigid O1 instanton. And in particular, these two properties imply that we have the most simple possible content of zero modes. There are just zero modes, 4 bosonic zero modes associated with translations of the instanton in 4-dimensional space-time, and 2 fermionic zero modes associated with the broken supercharges. Then I hope in the end of my talk also to consider a little bit more complicated situation where we have k identical D3 instantons wrapped on the same cycle. So in this case, the content of the zero modes is already a little bit more complicated, but we can also treat this case.
Do you have an explicit example of a Calabi-Yau threefold where this instanton is rigid, there's no multi-die space associated to the cycle?
Well, no, we didn't consider any, but I think this example should have appeared already in the literature because this is one of the basic, what people considered before, it seems to me. Yeah, we didn't specify to any concrete models, but I'm sure there are plenty of such examples. Okay, so how do we compute instanton contributions to string amplitudes? So let's consider one such amplitude where we have n insertions of closed string vertex operators, and we're interested in the instanton contribution to this amplitude. Well, then it's easy to realize that in the leading order in the small string coupling limit, the contribution will have the form of exponential of the instanton action, which is just the disk diagram with the boundary on the D-instanton. Then we will have the annulus amplitude, and then there will be product of n disk diagrams, each having one insertion of the closed string vertex operator. Of course, if we have orientifold planes, we should also add the contribution of the Möbius strip. But when you start computing these diagrams, you will immediately encounter problems. Like I said in the beginning of my talk, there will be some divergences due to various zero modes and so on. And just let's consider the most simple example where you have annulus amplitude in flat 10 dimensions. Then it's well known to be given by this expression. And on one hand, the integrand is 0 due to the famous theta identity, between theta functions. But on the other hand, if you try to integrate separately each term here, you will get divergence. And so you don't really know what's the result of this computation. Is it a 0 or some non-vanishing constant? So and this is a typical situation. And well, in the best case, you can compute your diagrams up to some additive contribution. But you see, since this diagram is exponentiated, really you have an ambiguity in the, well, in the best case, up to numerical factor in front. And that was the problem. So, as I told you, Ashok understood how to deal with these problems using string field theory. And he produced certain recipe. I won't explain his solution in full detail, but just give me, I will give you this recipe how to deal with the zero modes from what he understood. And it turns out that we need to distinguish various classes of zero modes. So first of all, there are zero modes which describe collective coordinates of the Dinstanton. I think sometimes they're called universal zero modes. So, and then they can be bosonic and fermionic. And the claim is that all these zero modes should be left unintegrated till the very end of the computation. So first you will have to combine contributions of all these diagrams and only then integrate over these zero modes. And if you proceed like this, then the claim is that integration of bosonic zero modes will produce just the momentum conserving delta function, whereas to saturate fermionic zero modes, you will have to insert the corresponding number of fermionic zero mode vertex operators into the disk diagrams. So for example, if you have 4 fermion zero modes, you will have to introduce, you will have to insert 4 fermion zero mode vertex operators. But that's not the end of the story, because there are other zero modes. For example, there are generically zero modes from Gauss fields. And those arise because of the breakdown of the so-called Ziegel gauge, which is typically imposed on string field theory to arrive to the usual Walsh-Schilf formulation. And it turns out that in the presence of D-instanton, this gauge is bad. So it's not well defined. So to obtain something well defined, you have to return to the original gauge invariant formulation of the path integral, at least in this zero mode sector. And then everything, well, becomes well defined, fine, and you can proceed calculating things. And finally, there are you can have other zero modes, and typically you integrate them with some nonlinear effective action which arises for them. Of course, it can happen that some fermionic zero modes are not saturated. Well, then you don't have instanton contribution. It means that it will vanish. Okay, so this is the recipe, and there are actually, in the simplest case of the rigid one instanton, fortunately there are no the last two types of zero modes, just the first one. So with this recipe we can compute our annulus and Möbius strip diagrams. And this is what we find. So essentially, there are three factors here. Well, first factor is just numerical factor, 1/2, which is easy to understand. It's just the volume of our symmetry group of 1, which has two elements. So we divide by these two. Then let's look in the end. There are these contributions over universal zero modes, which according to the recipe, which I just told you, should be left till the end of the calculation. So there are 4 bosonic zero modes and 2 fermionic ones. In particular, the bosonic zero modes will produce this momentum conserving delta function in the end. And the most non-trivial contribution is this function K0, which is actually the contribution of the massive modes, because in the n=1 case, supersymmetry is not enough to ensure the cancellation of bosonic against fermionic modes. So we have generically some non-trivial function here. And so here I gave an integral expression for this function. As you see, it involves annulus partition function, Möbius partition function, and finally there is the last term, which is leftover of zero modes, and it is this term which makes this contribution finite. So due to this last term, which we derived, one can prove that this integral expression is actually finite, and there are no divergences. And of course, what is very important is the coefficient in front. This coefficient is essentially an index, and well, it's easy to understand what it is. It's just the number of bosonic zero modes minus half fermionic zero modes. So this is how you compute it. So what is important is that this is a finite expression. Unfortunately, it's generically it's impossible to calculate this function explicitly, because for this you should know the open string spectrum on the D-instanton, and for generic Calabi-Yau it's impossible. But if you have some, for example, orbifold model which is integrable, then well, it's possible to do. And in principle, there are already results in the literature. Nevertheless, what we have done, we express these annulus and Möbius partition functions as a sums over representations of the underlying n=2 superconformal algebra. And it turned out that they are given by very simple sums of, well, essentially theta functions. So it turns out that there are a lot of simplifications coming from the combination of characters of n=2 superconformal algebra. In the end, you find a very simple expression. And but unfortunately, there are these coefficients NHQ. So the representations are labeled here by two numbers, H and Q. And these n's, they are, roughly speaking, number of representations appearing in the spectrum. So you see the spectrum is encoded by these numbers, and until you know it explicitly, well, we cannot compute the full partition function. But if you know, then, well, you just substitute and compute. Fine, so this is how we compute the annulus and Möbius string diagrams. And now let's turn to the effective action. And we're in a theory with n=1 supersymmetry. So generically, the scalars and fermions in this theory get masses. So here I show two terms in the effective action. The first one is the fermion mass term. The other one is the potential, which generically generates masses for scalars. And you see both terms are fixed by the Keller potential appearing in the kinetic term for the scalars and fermions, and also the function W, which is known as a holomorphic superpotential. So in particular, it must be a holomorphic function of the moduli. Now, I recall you that we do not include any fluxes, and in this situation, perturbatively superpotential is 0, but then we assume that there is a non-trivial instanton contribution to this superpotential. So it means that it will have the form of exponential minus instanton action times certain function A gamma, and the point is precisely we have to find this function A gamma. So how to do this? Let's substitute the superpotential into this fermion mass term and extract the leading order in the small string coupling limit. Then it's easy to understand that the leading order comes when these derivatives act on the exponential, because exponential is proportional to 1 over G string. So this is how you get these two factors here. And you get this contribution. Now, the presence of this contribution in the effective action implies that there is a non-trivial instanton contribution to the two-point function of fermion vertex operators. Yeah, these are vertex operators corresponding to these fields. So I copied the resulting expression for this contribution on the new page. And the point is that we also can compute the same contribution from our string instanton calculus. So as I showed you some slides ago, this is exponential minus instanton action, then there is exponential of these two amplitudes, and then since we are computing two-point function, there will be two disk diagrams, each having an insertion of these fermion vertex operators, but also since our rigid O1 instanton has two fermion zero modes, we will have to insert two fermion zero modes vertex operators. And it's easy to understand that the only non-vanishing contribution comes from the insertion when one goes to here and another to the second disk diagram. Now, we already computed this factor, and then one can also show that one can also compute the disk diagram in this case, and in particular note that it will be proportional to the derivative of the instanton action. And then you just combine all these factors together, compare against the first line, and from here you derive an expression for the instanton-induced superpotential. In particular, you see it comes with some definite numerical coefficient in front. Actually, there is a freedom here, because we can still do some redefinitions of the fields, and this freedom leads to the appearance of this phase factor, exponential of ixi, where xi can be a function of the moduli, but just real function. And so at this point, we see that there is still some ambiguity in this superpotential, in this result. But as I'll show you later, this ambiguity is fixed if you recall that this superpotential must be a holomorphic function of the moduli, and this allows to fix this ambiguity completely. But before going to this issue of holomorphicity, let's consider what happens if we consider multi-instanton effects. Namely, we wrap the same cycle several times. So I copied here the zero mode content, which appears in this situation. And one can look what happens with our main non-trivial contribution, namely exponential of annulus plus Möbius strip. So the result changes a bit. Well, first of all, there is a change in this contribution of massive modes. Well, essentially, there is a change in this coefficient, 3k. So this 3k is obtained like this. So the first number is this number minus this one. So minus because these are ghost modes, so they come with the opposite sign wrong statistics, and then minus half of Ramon zero modes in the Ramon sector. So this is how you get this 3K. But otherwise, well, this is still some non-trivial function. Then we still have the same universal zero modes, so we leave this factor the same. But most importantly, we have a new factor, which comes from the all remaining modes, which are not universal and not ghost. Okay? So as I mentioned in the beginning, in this case, well, it's given by integral over all the remaining zero modes, which are integrated with some, well, you see, nonlinear effective action. Well, here I just redefined these modes, introducing new notations, just to rescale the factor of open string coupling so that it doesn't appear in the effective action here. Now, let's look more closely at the resulting integral. Well, we have some bosonic modes, and then two types of fermionic modes. One's are undotted, and the other dotted. And if you count the number of these modes, you find these numbers. And if you calculate the difference, you find that the difference of undotted and dotted zero modes is non-vanishing as soon as k is larger than 1. But on the other hand, look at this effective action. Here you see that undotted and dotted zero modes, they come in pairs. So it means that you can saturate the integration of these zero modes only if there is equal number of them. But this is not the case if k is larger than 1, and therefore we have to conclude that for our rigid OK instantons, there are no multi-instanton effects. And this is in drastic contrast, for example, with the situation in n equal 2, where you saw there was some multi-covering factor taking into account multi-covering effects. Here there are no multi-covering effects. I should also say that this result is specific for this particular setup, where we have just one rigid cycle with this zero mode content. You can consider more complicated setup, more, for example, cycles which are not invariant under orientifold projection, are not rigid, and then you could produce multi-instanton effects, and this has been considered in the literature already.
Sorry, could I ask, the multi-coverings in n equal 2, are they also for rigid instantons?
No, there is no difference whether it's rigid or not. That's the power of n equal 2. You just, the properties of the cycle are not important.
But the invariance, the DT invariance,
Yeah.
is 0 for the higher ones, right?
No, the point is that there is, so if you have some cycle, so characterized by some charge, there is Donaldson-Thomas invariant multiplying it. But then there is a multi-covering effect, and they all come with the same coefficient, with the same Donaldson-Thomas invariant. Or you can trade multi-covering effects, like written explicitly. You can also introduce the so-called rational DT invariance, and this is equivalent to taking into account multi-covering effects. In fact, sometimes it's much more convenient to work with rational DT invariance. For example, if you want to see modular properties of, I don't know, D3 instantons, they're better seen in terms of rational DT invariance. Just an aside comment. Okay, so finally, let's go to the issue of holomorphicity. So why this superpotential is holomorphic? At first sight, it doesn't look to be holomorphic at all. Well, there is open string coupling, which is related to the real part of the instanton action. There is this horrible function K0, and so on. Well, in fact, it has been already understood many years ago how to show holomorphicity. So we just follow the path paved for us in these papers. And so essentially our contribution here is that, well, first of all, we understand what to deal with zero modes, so we can fix all numerical factors and so on. And second, we can show this for generic Calabi-Yau, well, where you can, which have this setup which I'm assuming here. So the idea to prove holomorphicity is based on a remarkable identity between instanton partition function and one loop threshold correction to the gauge coupling on a space-filling D-brane wrapping the same cycle on the internal manifold. So originally, this remarkable identity was noticed for orbifold models, but then it turns out that one can prove it actually for generic Calabi-Yau. So the idea is that on one hand, first you calculate these annulus diagrams with these boundary conditions. So, for example, Dirichlet on one side and Neumann on the other side, or the Möbius diagram. And then you compare it with the partition function where on one hand you flip one of the boundary conditions, so you replace Dirichlet by Neumann. And on the other hand, you also switch on some electromagnetic field B. And then you take derivative, second derivative with respect to B, set B to 0. And then it turns out that these two things, they're actually equal. You can prove it. And then it turns out that these partition functions, they encode precisely the contribution to, precisely encode this one loop threshold correction. So, and you precisely get this identity. And now we have this identity. And one can use now another fact that this one loop threshold correction has this generic form, which was found, you see, almost 30 years ago. So here I just adapted the generic form to our particular setup. And then well, according to our identity, this should be equal to the D-instanton partition function in the presence of an infrared cutoff. Infrared cutoff just introduces these damping exponentials in the definition. And you can show, easily show that this integral can be expressed through our function K0. So now you combine that this is equal to the first line. So you derive an expression for this K0 function through this function f1, which, as you see, is has interpretation as one loop correction to the kinetic gauge function. In particular, it's holomorphic. And finally, you substitute this function K0 into our expression of the induced superpotential. And now you note that if you choose that undetermined phase psi to be just imaginary part of this holomorphic function f1, what you find is a holomorphic expression. So superpotential becomes a holomorphic function of the one loop corrected moduli. So this is important that we have to take into account also one loop corrections to the moduli. But this is what we need to do. So in the end, we find an explicit expression which is holomorphic, where all coefficients are fixed. And so this is one of our main results. So let me just conclude. So the main message of my talk, you can take it like string theory is able to fix all ambiguities which appear in string diagrams in the presence of D-instantons. So now we can calculate D-instanton contributions in principle in any setup. And then in the n=2 story, so we found a very non-trivial match. On one hand, the prediction based on dualities. On the other hand, this computation done on the basis of these amplitudes. And then in the case of orientable compactification, we derived an expression for the instanton-induced superpotential. Now, how to proceed further? Well, first of all, one can just take our result and apply it in some phenomenological models based on string theory, which use this D-instanton-induced superpotential. And very often, well, people have to assume something about the weight with which this superpotential appears, namely the coefficient form. Sometimes they assume that it's of order 1 or it's very small. Well, now there is nothing to assume. You just take the result, you substitute, and you find what you get. Or one can proceed with some extensions. One can consider more complicated types of instantons rather than just rigid or one. Or one can include fluxes or go beyond the leading order in the string coupling. And finally, one can also ask, can we do such computations maybe for other types of instantons? For example, already in the n=2 story, so just type 2 on Calabi-Yau, there are still NS-fibrin instanton effects which contribute to the hypermultiplet metric. And so far, we were not able, just using dualities, to completely understand these instanton contributions. So this, they remain like the last missing piece of the full picture. And so maybe, I don't know, if somebody can generalize this technique to compute NS-fibrin instantons, this will shed light on a very important issue. So let me stop here, and thank you very much for your attention. Well, I'm not sure because, generically I wouldn't expect this result will persist because, well, it's requires, how to say, as soon as you switch something new, there is a big chance that you can saturate zero modes. Well, I'm not 100% sure, but I don't know. One should look at the concrete setup and see what's going on.
Also, in concrete setups of oriented field compactifications, you will also have D-branes in the geometry. So this certainly would also contribute to your analysis amplitudes, or you are only considering models where you neglect, so to say.
One can say that we consider it, so this will introduce dependence on open string modeling, so one can say that we concentrated on the contribution coming from closed string modeling. But generically, one should compute this also. Sorry, which phase do you mean? This phase which I fix on?
So if you have multiple contributions and you sum them up, sometimes they can cancel.
So what's the question? I didn't understand.
What specific structure? How do you translate this cancellation into the properties of this F1? So for some reason, that these different F1s have to be aligned such that when you sum them up,
well, I don't see what. Well, here I don't see really cancellation. I'm not sure which cancellation you are talking about, because here there is no real cancellation, just combination of this imaginary part with the real part.
You only get a single contribution, but if you get contribution, can you get contribution from multiple instantons with the same prefactor such that they cancel when you sum them up?
Well, again, in our setup, they vanish just due to non-saturation of zero modes. So it's not that something cancels really. And this factor, well, I'm not sure what you mean, because this factor appears in the exponential, so I don't see which cancellation you, maybe I don't understand really the question. Yeah.
That's true, but you would have to know more about the details of the Calabi-Yau compactification, and then you would, you might know something about the spectrum in that case, and then you would just plug into these formulas, and there would be some check. This is very related to the question that I'm trying to ask you during my talk, which is, what if you
last maybe question. In the n equals 2 case, there's corrections to the metric, of course. Now you do the Orientifold, you break SUSY. I would expect still there to be instanton contributions to the Kehl potential.
Yeah, sure. No, we just didn't consider, but for sure there are.
They will correct.
Yeah, I believe so, and probably some of them, well, you partially, yeah, you did some work trying to reduce, yeah, from n equal 2 to n equal 1, some corrections. Maybe there will be some new corrections just from pure n equal 1. Yeah, it's a very interesting story, but I'm not sure there are some detailed studies of this.
One short question. So just to clarify, the field phi, so you in type 2B Orientifolds, and the field phi is parameterizing or is a modulus.
Yeah.
Do they include complex structure moduli?
Well, in principle, here by phi we mean all the moduli. Yeah, of course, in reality, when you consider, for example, the 3 instantons, typically the instanton action will depend just on the Keller moduli. Yeah, but but for example, the function K0, it will depend generically on all moduli. Yeah.